All right, done.
Okay, great. My name is Raghava, and I am an assistant professor in the computer science department at IIIT-Delhi. And so I have been working at IIIT-Delhi since September 2018. So it's been almost 4 years. And so my primary research area is semantic web, and within that I work in ontology, modeling, reasoning, and knowledge graphs as well. And all these things are based on description logics, which is a subset of first order logic. Right? So in this course, as it's called, so I will be having 3 topics, right? But all of them, the basis for all of them is description logic. So I start off with description logics, gives a brief introduction of it. That's the first part. And in the second part, I will be talking about what is called as OWL, which is Web Ontology Language. Right? The acronym is OWL. That's the second part of it. And in the third part, which I hope is a lot more interactive, is we'll be doing some modeling together. So we'll be building an ontology together. So you can give me your suggestions and inputs, and we'll be doing that. So these are the 3 parts, and it will be spread across 4 sessions. This is the first session, and we'll have one more in the afternoon today, and again we'll have the same thing tomorrow. So there is one session in the morning tomorrow and in the afternoon as well, right? So these 3 topics will be spread across these 4 sessions. So right towards the end of probably today, I'll be giving you some links. So you can say there's something called Protege, which you can use to build these ontologies. So hopefully all of you can install it by tomorrow, and it's pretty easy to install it, right? So, and we can all do the ontology modeling together sometime tomorrow, either in the morning or in the afternoon. Okay, so that's the general plan for the course across the 4 sessions, right? And okay, so now let's get started. So I'll briefly start with the context, right? So I'll talk about the context and where this can be placed, the topic of description logics can be placed, and in general, the semantic web. So we won't be, so most likely I won't be using the term semantic web too often, but that's my primary area. But the standards, they are all based on description logics. Okay. So by now, I think you would have known about artificial intelligence, and you would have probably worked and used lots of devices that make use of AI. Right? So although I give these general definitions and descriptions, you are already aware of it. Right? So something like, so the idea is to mimic the intelligence of the humans, which is what is called as the natural intelligence. Right? So you have the natural intelligence, and then we make use of these sensors that we have, the 5 senses of that we have, which is the sight, sound, touch, smell, taste, right? And then we perceive the environment, and based on that, we can take a decision, or we can give a suggestion, and so on. So we react to our surroundings and take the context into account, and then we give out, we take a decision, right? And that is what the idea is in artificial intelligence as well. We try to mimic what we do, so what the humans do. And as you are aware, there are lots of applications of these artificially intelligent agents, right? And like I said, you will very well be using several of them in your day-to-day life. So things like let's say intelligent assistants, so they can be on your phone, or they can be in your home, something like Siri, Cortana, Google Home, and so on, right? So there is games. So a computer chess game bet a human several decades ago already, right? And a few years back, AlphaGo was very popular. So it was able to beat the top human Go player. So, and Go is supposed to be a lot more complex than chess. And chess itself is complex, but again, Go is supposed to be several levels higher in terms of complexity than chess. Right? So and there's this targeted advertising, so which is like personalization. So the advertisement that you see may not be the same as what your friend sees, even though you're using the same application. Because the things that you do other than within that application, and let's say the ones that you do on the device, they influence the sort of advertisement that you get. So these are, and it's very popular in the healthcare and biomedical domain. There are lots of uh, very useful applications like radiology. They detect the images and then they give out the summaries. Um, then then there's a lot of push towards cancer detection and so on. Right? So this is a field that is pervasive across different domains and applications. And now, in order to accomplish these different things and implement these different things, and like I said, we need to mimic. The idea is to mimic the things that the human does. Right? So you need different subfields within AI. So, for example, humans can, okay, assuming that there's a common language, we can understand each other. Right? We know the syntax and the semantics of the natural language, and we can understand each other, speak with each other. Now, in order to imitate that, we have a subfield of AI called natural language processing. And then there is something called the learning based techniques, which are very popular. So you have machine learning, deep learning, reinforcement learning, and so on. So again, these mimic certain aspects of the human. So for example, we learn through examples. Right? So for example, let's say um, uh, there is, so okay, when we did not know about fire, um, and when we touch something hot, we immediately take our hand back, or and then we realize that this is pretty hot. So next time we'll be very careful. Right? We'll be careful. We'll get to know what are the things that are hot or that are cold, and we'll try to take necessary precautions. So we learn through our experiences, and that is what generally machine learning tries to accomplish. Right? So which is what is called a supervised learning. So you learn the patterns based on certain examples, and then you apply it to newer scenarios. And then there is, of course, a computer vision, which is like which will try to mimic what our eyes do. So we try to look around, visualize what is happening, and then take decisions based on that. And there are other fields like robotics, which you might already be aware of, and then there's neural networks, which again tries to mimic how the brain functions. And among these things, the one that is of our interest is the one that is highlighted, which is knowledge representation and reasoning, and that is what we'll be focusing on. So that's the context in which whatever I'm going to talk, that will fit in. Right? So this is a subpart of AI, at least, okay, from the semantic point of view, but this is based on logic, and that's where the connection is with respect to the ISLA. Right? Okay, so we'll talk about knowledge representation and reasoning first, and then get into description logics. Right? Okay, so again, so everything, like I said, is connected to the way we mimic humans, and knowledge representation and reasoning is, again, it's based on the similar theme, where the idea is to capture the facts which are out there in the world, and once you capture them, you can draw some inferences based on these facts. Right? So let's say and you can learn these facts in multiple ways. So let's say as a human, you can learn about the world by reading a book, or by talking to another person. Let's say you talk with your mom, your siblings, and you get to know more about the world. Right? The world could mean anything. So it could mean your school, it could mean the way movies made, for example, or the way the roads are constructed. So it could mean different things for different person, and in general we call that as a world. Right? And it can also be something that's common across the world. Let's say sunrises in the east. Right? These again a fact that you get to know either by reading a book, by observing, or by talking to people, watching TV, and so on. So there are multiple ways of getting to know these facts. And the idea behind KRR is that you again capture these facts in a way that the machine can also understand. So now if the machine knows more about the world, it can take more informed decisions, right? Say, for example, whenever I say the term car, you will know what exactly I mean, right? So you can get the picture of the car in your head, and you also get to know these connections. So maybe you can recollect the good experiences that you had with a car. So maybe you went on a long drive, maybe your first car driving experience, your first car or something. Right? So all these experiences you can recollect, and these are all connected together. But for a machine, it doesn't know anything about a car, right? So if you say car, other than the string, that this is a 3-character string, it's a C, A, and R, it doesn't know much about it. So if we can give more information about it, let's say something like car is car has exactly one engine, right? And car is something that has at least 2 doors and at most 4 doors. And car is a type of vehicle. So now we are building up more and more knowledge about the car that the machine can make use of. By machine, I mean any intelligent agent, right? Any software. And so we are able to also make connections between different concepts here. So now there's a concept car, there's a concept called vehicle or a wheel, and we are trying to make a connection between these concepts. And that's what we'll be doing in the rest of the sessions as well, right? So we'll try to pick up these important concepts, and we'll try to make these connections between these concepts, and that's how we model the world. And description logics and all these, they are tools that we can use to model the world, right? Okay, so now that you have this information, so this is what is called as the knowledge representation part. You have, this is captured in a way that the machines can process, right? So that's the first part, the KR part. And then the last R stands for reasoning. So once you have some information, you can easily draw inferences, right? So an example is given here. So let's say you are given 2 facts: all birds fly and pigeon is a bird. Now, if you are given these 2 facts, and if someone asks you a question, can pigeon fly? You can easily answer it, right? So since pigeon is a bird and birds can fly, so you can deduce that pigeon can also fly. But that is not the case for machines. So unless you explicitly state that pigeon can also fly, it cannot answer that question. So what if we can enable this facility or this feature by using these reasoning mechanisms? So you already captured this knowledge that all birds fly and pigeon is a bird. But now using this knowledge, we can also draw some inferences. And that will help the machine to answer additional questions, right? So something as simple as, let's say, okay, I'm from IIIT-Delhi, right? So Raghava works at IIIT-Delhi. IIIT-Delhi is located in India. Oh, sorry, IIIT-Delhi, maybe you can say IIIT-Delhi is located in Delhi, and Delhi is the capital of India, right? Now, if someone asks the question, where is Raghava located? It's indirectly, we can indirectly make an inference that I'm located in Delhi, right? Because I work at IIIT-Delhi and it is located in Delhi. So obviously there's a high chance, okay, pre-COVID days at least, there's a high chance that I will be in Delhi, right? So those are some of the answers that can be drawn based on inferences, which is not possible if you, without the inference, you wouldn't be able to answer that question. The question that I asked, which is where is Raghava located, right? Okay, so that's the field of KRR in general, and like I said, we'll be talking more about these mechanisms to capture the knowledge. And this is obviously, and even for humans, is very useful to get to know the background knowledge so that we can take informed decisions, right? So unless you know, let's say you are buying a car, so if there are 3 or 4 different models that you are considering, unless you know about each of these models, you won't be able to make informed choices, right? And in order to know about each of these models, you will again improve your knowledge or build up your knowledge by reading about each of these car models. And that's what is happening here. So unless we put in these background knowledge for the things that we are interested in, it will be, or it will help in making more better decisions or informed decisions. Okay, so any questions so far?
Yes, I have one question. So just can you please go back to the previous slide? Yeah, so like we have knowledge, which is like car is a type of vehicle and it has four wheels. Now, if this knowledge is actually captured from the web or some data source, or we as the programmers or who is building this database, or we have to code these rules. So how does it go? Because sometimes it
Hmm.
may happen that that kind of knowledge is not available. So what? How do we proceed?
Right, right. Okay, that's a good question. So I'll be talking about that briefly in, let's say, the third, while
Okay.
discussing the third topic, which is on ontology modeling, right? So that's where we'll actually be capturing the facts in a way that the machine can process. So there are a couple of ways. The uh, so the classical or even the best mechanism is to sit with a domain expert.
Okay.
So there is, so for example, you want to build or capture these facts about cancer, right? The example that I gave. So, or neonates or some field of healthcare which is very specialized. So then you would have to take the help of the domain experts. And generally, it's an iterative process. Right? So you go and meet the expert, um, and get and explain the application that you want to build, so that you can scope the knowledge. So one thing which I think which is okay, it's a uh, sort of a cliche, but it's and I think all of you are aware of it. So knowledge is always incomplete. It is no way that you can capture all the knowledge in the world in one place, right? So it's always incomplete. So let's say you try to capture the knowledge about a university. So unless you define the scope of it, it's hard to capture everything that is part of the university, because there are lots of different things. You may be interested in the courses and the faculty and so on, but there is the administrative aspect, right? And there's the building construction and so on. So there are multiple aspects, but we should scope it.
So
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 the
the
best way, okay, sorry, I guess, so the best way is to sit with the domain expert and capture this information. The
so
other
the
mechanism is to there is ongoing research on trying to do this automatically, or at least semi-automatically, where which is the um, use case that you suggested, right? So you have the web pages, and now web pages already capture lots of information. So from that information, how can we extract these kinds of knowledge and put it in a form that the machine can process? So that's like ongoing work, but the disadvantage is that it's not, the quality is not that great, but it can scale. On the other hand, if you do it manually, the quality is very high, but it doesn't scale. So that's the trade-off. Yeah, yeah, yeah. Sorry, go ahead. You can go.
Thank you. So basically, what why I was asking this question is that I have been attending, these workshops, but incidentally, I happened to attend an advanced workshop before going to the basic one. I somehow enrolled for the wrong one, and I wanted to use this field. So I just wanted to understand that that means we are not constrained by the fact that we only have to use the web. So there is some hybrid kind of approach that we could adopt, like talking to the domain experts or maybe using the web. So like in machine learning, we normally use data sets and CSV files and JSON files. So can this be done? Can those data sets can also be used
Mhm.
in this particular KRR representation?
Yes, yes. So for let's say, okay, so generally it is the case that the domain knowledge is small in size, but the instance data is large, right? So for like going by the CSV example, let's say, okay, so in one of the projects I'm working on air pollution related, building an air pollution related application. Now air pollution, so there is, you get air pollution data from the sensors, which is generally in CSV format. But air pollution is also dependent on multiple other factors. So let's say one of them is weather data. So if there is rain or if there is strong breeze, the pollution at that particular spot is not that high, or in that particular area. So it's dependent on weather data. So you should also, for example, collect the weather data, which is in, again, it could be in CSV format or JSON or XML format. Um, then you have the, let's say, the industries. So if there are industries and their wastage, so you can collect that data as well. So that's again a different type of data, but all these are related to each other. So you can build a ontology or a capture the knowledge which can relate all these things. So there is a connection between weather data and pollution data, which is the PM 2.5 levels or the PM 5 or 10 level, right? And the different gases in the air. So you can capture the relationship, and then so CSV files might have, let's say, thousands of rows, but the relationships between these concepts, they may not be that high. So for example, you may be, there could only be 100 different concepts and maybe 20 different relationships between these 100 concepts. So you capture that manually, but then you can use this CSV files to say that a column 3 is related to the concept X in the knowledge that we captured. So we can talk about it while building the ontology. Right. So I don't explicitly cover the mapping part, but we can briefly talk about it later on as well.
Thank you. Thank you.
So yeah, the takeaway is that the schema knowledge, if you compare it with the relational databases, for example, so you have these ER diagrams where you talk about the relationship between the tables, right? So let's say there is a table on courses, there's a table on students, and there's a table on faculty members. And if you talk about course registration, all of them are related, right? So students register for a course and faculty teaches a course. So all the three are connected, and the connection is captured in the ER diagrams, which is what is called as a schema for the tables. But the actual rows or the actual data sits in the table, and that's in the, let's say, the CSV format or JSON format or whatever, right? So, and now you can make a connection between the instance data and the schema knowledge, and that's what we do here as well. So generally the schema knowledge is small and the instance data is quite large. Okay. And you can make a mapping between these two.
Great. Great. Thank you. Thank you.
So one of the, which I don't again talk about here, is one of the important applications of these ontologies, and okay, I use another term called knowledge graph, but I don't talk about it here, is data integration. So you can easily integrate the data from sensors with the weather data and the one from the industries, right? So that you can create a common structured representation. And structured representations is what is part of these knowledge representation. Right? You capture this information in a structured way so that machines can process it. So that's one of the important sort of application. Okay, so I'll move on. There are different mechanisms to capture the knowledge, and we'll be focusing on this part of it, where we use logic, and in particular first order logic, and a subset of it, which is what is called as description logics, right? And ontologies is something that is, okay, I don't talk about RDF in this particular course, but both these ontologies, which is you use OWL, I'll talk about OWL later on. We use OWL and RDF, which are based on description logics, and description logics itself is a subset of first order logic, right? So we'll stick to the logics based mechanisms for capturing the knowledge, but there are other mechanisms as well, right, which we don't talk about here. Okay, so that's a brief context where we are coming from, right? So description logics, I'll talk of description logic from the context of knowledge representation reasoning, which is a subfield of AI, right? So that's the connection. Okay, so let's get started with the actual topic, which is description logics. So most likely I'll be talking of description logics in this particular session and in the afternoon session today, right? That's the plan. And most likely tomorrow I'll start with OWL, which is the web ontology language. It's a language used to construct ontologies, and later on we'll take up one particular use case and build the ontologies together, right? An ontology together. Okay. Okay, so description logics is a mechanism to capture the knowledge in the world, and that is what is called as knowledge representation, right? And it provides the formal underpinning. So that means that's the basis on which OWL and RDF are built upon. And description logics itself is a fragment of, or it's a subset or a piece of first order logic, and that's the connection with the school, right? So with the ISLA, So it is all logic based, and that's why it's a appropriate topic. So these are decidable fragments, and what we mean by a decidable fragment is, given a problem, no matter how long it takes. At this point, we don't care about the performance of the algorithm itself, right? But it can take any how much our time it wants to. But at the end of it, it should be able to give an yes or no answer. Say, for example, finding whether the given string is palindrome or not. Right? So the palindrome should spell the same way, whichever in the forward or the backward direction. Right? Something like A B A. So no matter which way you go, or in terms of numbers, it could be 101. Right? So it's a palindrome. So if the question is given a string, can you check whether it's a palindrome or not? The algorithm should be able to answer yes or no, and that's the decidability problem. Right? And description logics make up the decidable fragments of it's a decidable fragment of first law logic. Okay. Now the advantage of using description logics to capture the knowledge representation part, or to capture the knowledge, is that it has a formal semantics. And so you can easily prove or disprove something. And there are constructs. So constructs meaning something like let's say disjunction, conjunction, implication, by implication. So these are all constructs that you can use to relate things. So for example, you can say that um, let's say has son is a subproperty of has child. So if A has son B, then it means that A has child B as well. So it's a subproperty which is similar to implication. Right? So these are, so it has, it's based on first order logic, and first order logic already has lots of so it's well proven, like the constructs and their meanings. It has fixed semantics, and there are also lots of tools that were built using these, so you can use these theorem provers and so on. And so okay, and there are also several optimizations that were already done, right? So it's the idea is that you are starting from something that has been in existence for a long time, and it's well established. So it has a strong grounding, as so to say. So that's one of the primary reasons description logics were used for uh, capturing the knowledge, at least from the semantic web point of view. So please be aware that semantic web is sort of a recent field, right? So it started maybe 2022 or 25 years back at the most, and it's not a huge amount of time when you, especially when you compare it with first order logics and logics in general. Okay, and the other advantage which we talked about is that if you use logics, it is easy to draw these inferences, and these days there's also an important field of AI called explainability, where it's important to also explain the decisions that were taken by the machine, right? And if you use logic or ontologies or anything that's based on logic, it's very easy to show how the fact was inferred, right? You can just go back and then check, because everything is has a specific meaning and a specific step that you follow, a sequence of steps, so it's easy to infer things and also explain it. Okay. But there are obviously other choices that could have been taken to represent the knowledge. So, for example, you may be aware of entity relationship diagrams, which are used in relational databases. And there's the UML, which stands for Unified Modeling Language, right? It is pretty popular, especially for in the software code or software engineering applications. So you have um, mechanisms where UML can be used to show the flow of activities and the code in general. So there are obviously other ways of modeling things, but description logics, or DL in short, offers these advantages where it has these formal semantics, and most importantly, it can be easily be processed by machines or any software agent, right? And the other advantage is we can represent complex relationships. So an example of a complex relationship is the uncle example. So my father's brother is my uncle, right? So that means the way we represent that is, if A has father B and B has brother C, then that means A has uncle C. right? And you can represent or capture these complex relationships using description logics. Okay, so there are two important assumptions that are followed in description logics, and anything that's based on that, right? So OWL and RDF also have these assumptions or follow these assumptions. So one is called the open world assumption, or OWA in short. So in general, we are used to closed world assumptions. So let's say in a relational database, you have um, um, this fact: Italy is part of Europe. Now, if you ask the question, is Spain part of Europe? The answer would be a no, right? You can write a SQL query uh, for the relational database, and it will give you an empty result because you did not specify that Spain is part of Europe. That's the closed world assumption. That means if it's not known, then it should be false. Anything that's not known is false, right? Anything that is known is true. So you, because you know it, obviously, but the something that's not known is false, assumed to be false, because in the closed world assumption, the sort of the implicit idea is that knowledge is complete. In the open world assumption, the implicit sort of the assumption is that knowledge is always incomplete. So at any point in time, there can be an addition of knowledge, right? So if, so for the same example, if you ask, is Spain part of Europe? And this is in the closed world assumption, the answer would be unknown, or I don't know, right? Spain at this point, I know that it may not be part of Europe, but at some other point, if I have more knowledge, I can answer this question. So I would say that it's unknown, right? So that's the open world assumption. That means anything that is not known is unknown rather than false, and that's the assumption that we take in ontologies and RDF as well. Okay, so okay, I gave this example already, right? So CWA is obviously very useful in lots of applications. So let's say you have a flight booking application. You are trying to book through, let's say, Air India, right? And now if you look for a flight between X and Y, let's say between Delhi and I don't know, Greece, somewhere in Greece. Now, unless it cannot give an answer of unknown to you, right? It cannot say I don't know. Either there is a flight between these two destinations, or there is no flight. Either there is availability of a seat in one of the flights, or there isn't. Right? So it cannot be the case that it can give you the answer of I don't know or unknown, and you will be satisfied with it, because you want to have the closed world assumption there. But there are situations where open world assumption is important, or it's important to have the open world assumption, especially if you are trying to model the knowledge that is out there in the web. So there's lots of information, and so if you try to model a particular aspect, you won't be able to capture all the knowledge that is out there. So let's say, again, going back to the university example, you can capture the knowledge about the courses, the students, but if there is a question on something that is not part of that, let's say something related to the administrative policies, then the answer has to be I don't know, right? You cannot give a yes or no answer concretely. And the other thing is, the data is obviously always changing. So let's say you take a Wikipedia page. Now, if that's something that is new, or even if it is very popular, in these two cases, the data is always changing on that particular page. Right? You keep adding more and more information to it. Something like World Cup, right? So in the World Cup, whichever World Cup you take, it could be Cricket World Cup, or it could be a Grand Slam, tennis Grand Slams. So every year it will get updated, right? Or whatever is the duration. So let's say for the World Cup, maybe every 2 years or every 3 years, it will get updated. So the information on that particular page is changing, and there could be wrong entries with the editors correct and so on. So there is sort of the implicit open nature associated with these kinds of scenarios. And there are scenarios where closed world assumption is best suitable. So both of them, there are scenarios where both of them are useful. So we need to pick the right tool for the right scenario. Okay, so that's the first assumption. And the second assumption is the no unique name assumption. So in general, when you assign names, which is also the case with the humans, right? So let's say you have two names, let's say Raghava and say something like Sumit, right? So Sumit and Raghava, they are, if someone says Sumit and Raghava, you assume that they are two different people, because the ID, the identifier in our case is our name, right? But that's the unique name assumption. But here we follow the no unique name assumption. That means unless explicitly stated that they are different, we don't assume that they are different, and neither do we assume that they are same. So that's the assumption here. So let's say Italy and Spain. Italy is a country, Spain is a country. Now these are two different names. Italy and Spain are different, and under the unique name assumption, where you follow closed world assumption implicitly. So we know that Italy and Spain, or we can say that, we can confidently say that Italy and Spain are different. They're different entities, and in this case, they're different countries, right? But so it's the other way around. So we'll have to say that they are same. For example, India, Bharat, right? So Bharat and India, although they are different names, we mean the same. So we need to explicitly state that they are the same. Otherwise, the assumption is that they are different, right? So, but in no unique name assumption, it's not the case. So, say for example, you take this. So Raghava works at IIIT Delhi, and then Raghava is also giving a talk as part of ISLA. So now, if there is a database where we are capturing, where we are recording these events, and we are capturing that information, like who are all the speakers, the participants, and the location of these videos, and so on, we can make a database out of it, right? So there'll be a Raghava inside that database as well. There's a Raghava inside the database of IIIT Delhi as well. So the names are the same. Unless we say that they are same or different, we cannot assume one way or the other. So that's the no unique name as an assumption, right? And those are the two assumptions that we follow. Okay, so these are connected. So unique name assumption and open world assumption, they are connected, right? So and because of the, I also gave this example. So let's say this is the example where we take Delhi. So if I took the example of Raghava, right? So let's say we can't say that they are the same or the different unless we explicitly state that, because again the information can be, or the knowledge can be captured by two different, in two different by two different entities, which is ISLA and IIIT Delhi in this case, and they can be for different purposes. The structure could be different, so we'll have to explicitly state whether they are the same or not. Okay, so those are the two different assumptions, and if there are any questions, I can take it. If not, I can move forward. Okay, so let's go ahead. So there are certain basic building
I
blocks.
have a question. Hello.
Yeah, yeah. Hi, Sai. Go ahead.
Yeah, just for clarification, so for in closed world assumption, UNA is followed means there both the Raghava will be the same, treated as same, right?
No UNA, so it's NUNA. Oh, in closed world assumption, yeah, yeah, right. So since the names are the same, yeah, they are
Without
assumed to be same.
explicitly
The
mentioning,
entities,
remains to
yeah,
be the same.
right. We can say that both these entities, since both are named as Raghava, they are the same in closed world assumption and unique name assumption.
Oh,
Okay, so there are three basic entities that are considered as building blocks for in description logics. So I also try to make the connection with the FOL and RDF, but I don't know, depending on your background, you can either ignore it or make your connections, right? The mapping. So there are three concepts. One is individuals, which is same as constants, but like I said, we can ignore this part because, yeah, if you're familiar with astrology, you can make these connections. So there are individuals, concepts, and roles. So we'll discuss each one of them uh, here. But before we go there, we can just briefly talk about the naming conventions. So individuals are, in some ways, they are the instances or the constants, right? So let's say if I say that Raghava is a type of faculty member, so Raghava is an individual here, and faculty is the concept. So individuals generally they are written in lower camel case. So let's say you have two words as part of the individual. So you have the first letter of the starting word is small letter, but the rest of the letters in the subsequent words, they are capital letters, like Rudolph here. Concepts, we follow the camel case. So if there are multiple words in the concept, each of the first letters is capitalized. And even for roles, we follow the lower camel case, like as daughter, as son, and so on. Okay. So now we'll also look at the description logic syntax, but most likely we'll not be using it anywhere, right? Like later on, we'll be looking at while building the ontologies, we'll directly make use of a tool called Protege. But let's say if you want to write it in a paper or discuss with others, so this syntax comes in handy because it's concise and you can use it. Okay. So when you say person within the parentheses, when you write Mary, this means that, so this is called a concept assertion, right? That means we are saying that Mary is a type of person. So person is the concept, and there can be many persons, and out of which one of them is Mary. So there's also a mapping with the set theory. Right? So you can assume that the name of the set is person, and set elements. So there are multiple elements that make up the set, right? And one of the elements is Mary. And when you say that, okay, we'll talk of the subclass later on, and that can be mapped to subset. Okay, so this is a concept assertion, and you have the role assertion. So here, this syntax means that John has wife Mary. So John and Mary are two individuals, and they are connected to each other by the has-wife relationship. Right. So you can ignore the RDF mapping here because we don't discuss it now. And this is the role assertion, right? So there are different types of these. So any fact here is called an axiom.
Yeah, Raghava.
Yes.
So concepts are unary predicates, and roles are binary or tertiary or quaternary predicates. Is that true?
Right. Yeah. So yeah, with the first logic, yes. So these are unary predicates, and then roles are binary.
Or we only allow binary. There is no tertiary or predicates.
No.
Only binary. Okay.
Binary, yeah. So the way it is, for example.
And what is the reason why individuals and roles have the same syntax? Like they start with the same small letter and camel case.
Okay, so I'll answer the first question and then come to the second one. So yeah, binary predicates are only allowed, but you can sort of, so you can say that John has wife instead of Mary. You can have a more complex sort of individual, right? In the sense that okay, so let's say so A is related to B and C is possible, but the C can be again slightly complex. So it need not be a single individual or a single concept. So let's say parent is someone who can be either a father or a mother can be a parent, right? But when you want to define mother as well, you can say that mother is someone who is a female and has a child or has at least one child, for example. So it can be complex. So you can sort of have this a mix of compound ones and atomic ones. So there's atomic concept and compound concept. Right? So compound concepts can be a mix of atomic concepts. So in that sense, you can, at the high level, yes, it's binary, but you can have sort of compound mix within this.
So if you want to say, let's say A, B, and C are triplets, how will you write that?
So then you can, okay. So eventually you can boil everything down to a binary relationship, but the C can be slightly more complex, right? So for example, you can, in the example that I said, so let's say B is related to A and B, sorry, B is related to A and C, but C can be a mix of D and E as well. So C can be, let's say, D union E or something.
I think it will be once we
okay.
move ahead,
Yeah. So maybe later on when I give some examples, I'll have some examples later on. Then I think it can it might, whatever I said in the air, it might be more clear there. Okay. So the other question that you had is why these conventions, right? Okay. So that's a good question. So I'm not okay. So there are two answers. One is I don't know the exact answer. The other is a sort of a educated guess, right? So generally, camel case. I mean, there are only two variations. So you have the lower camel case and the upper camel case. So unless they have a different, unless we come up with a different syntax where or different convention where we can use say underscores or move out of camel case, these are the only two possibilities, right? So we maybe they just stuck to it, but I'm not aware of the exact reason why only the camel case is used. For example, they could have used, let's say, for individuals some underscores. So you can say Sebastian underscore Rudolph and use lower camel case for roles. That's a possibility, but which is generally used. So these are only conventions, right? But you can move away from them as well. But these are the general conventions that are followed. So I don't know if that was helpful.
Yeah. I mean, my question was really concepts and roles are both predicates. So if we are using uppercase for concept, then why don't we use uppercase for roles as well? That's really the gist of my question.
I see. Okay. This is only for the role name. Yeah, okay, but yeah, you're right. You're right. So that's just the convention that people have come up with for description logics. But so on the other hand, right? So when we write it in symbols, so in the sense that okay, we don't use these explicit names when we say R1, R2, R3, we actually use capital letters. So let's say in these publications and all, when we talk of concepts and roles, so concepts could be something like, let's say, C1, C2, and Cn, they are capitalized. And roles as well, when we say R1, R2, Rn, they are also capitalized. So in those cases, we do use capital letters actually. Yeah, but when we write out the actual names, it's, I don't know, maybe this is easier to just differentiate between these two or something. I don't know. But yeah, lower camel case is used for roles when we do the actual modeling in terms of when we are building these ontologies. Is that okay? Can I?
Yeah.
Okay.
Yeah.
Okay. So largely, when we build these, so these are called as knowledge bases. It's similar to databases. These are also a database, but it's a database of knowledge. So that's why it's called a knowledge base. So the knowledge base consists of these types of assertions and the schema level or slightly abstract level knowledge, where you talk about the relationships between concepts, right? So something like, let's say there's a relation between employer and employee. So let's say Raghava is an employer and he is employed by IIIT-Delhi, right? Now that's the instance level data, which is what is called as the concept assertion and role assertion, right? So Raghava works at IIIT-Delhi is a role assertion because work set is the role that connects Raghava and IIIT-Delhi. But Raghava is a type of faculty, is a concept assertion. So all these assertions, they make up what is called as the assertional knowledge or the A box. Now, the relationship between employer and employee is more abstract, like one level higher, which is what is called as a schema level knowledge. And that is called as T box or terminological knowledge. So there is T box, A box, and in some cases you will also have one more categorization, which is called as R box, which consists of the roles. So things like has son is a subproperty of has child, and there is a relationship between father brother and uncle. So all these are what are called as role assertions or R box. Okay. So now, so I was trying to connect or map these things with set theory, right? So here the symbols are also pretty similar, except some minor differences. So here it's more of square shaped, where and in sets it's more rounded, right? So but so you can assume that, or you can safely map it. So woman here is a sub, you can, the way it's read is woman is a subclass of parent person, and you can map it to sets saying that okay, woman is a subset of person. So all the elements, which means all the instances of woman, are also, should also be instances of person, right? Which is what a subset means. Okay, so we call this as concept inclusion or subset or subclass. Women is a subclass of person, and there is also the equivalence. So equivalence is subsumption in both the directions. So person is a subclass of human, and human is also a subclass of person. So if you have it in both the directions, this is what is, this gives the equivalence. And if you want, we can also map this to first order logic. So this is same as implication, right? So women implies, so there's an implication, which is the if then part. So if someone is a woman, then it also means that they are also a person. So this is the implication, this is the by implication. So person is subset of human, and human is subset of person. Okay, so and these are what are called as T-box statements. So these are schema level knowledge, and we don't talk about instances here, right? So that's the T-box. And largely knowledge bases consists of these T-box and A-box, and in some cases they also come up with R-box. But so depending on the let's say the research paper that you're reading, either R boxes are part of A box, or they also have separate categorization, which is called R box. But if there is one, then R box consists exclusively of all these relationships. So let's say has wife is a sub property of has spouse. So if A has wife B, then it also means that A has spouse B, right? And there is, similar to concept equivalence, we also have role equivalence, and this is what is called as a composition. So you can have composition of any length, right? So here we have composition that is where there are only two roles involved, but it can be a chain. So it's also called a role chain. So if A has father B and B has brother C, then it means that, or it implies that A has uncle C. So that's how we can read this. And this is what is called as the R box. Okay. Again, so I tried to do this mapping, but you can again safely
May I
ignore it.
interrupt?
Sorry. Yeah, go ahead.
So there is, like, we are talking about role equivalence and the class equivalence, like person and human. So they are defined, both of them are defined, or we can use them interchangeably. Like we
Okay.
have
So here, okay, right. Okay. So yeah, both of them have been defined, but let's say if you are making use of a reasoner, right? I talked about these inferences, and there's a software called reasoner that can take in these facts and it can draw these inferences. So internally, reasoners, they do make use of the optimization that you talked about, right? So for example, wherever there is human, you can replace it with person. So now you don't have to deal with two different concepts, you can only deal with one concept, and that's sort of an optimization. But yeah, they are interchangeable, or you can replace one with the other. So does that answer the question?
so for example, like I have person and human, so there is an equivalence. But suppose I'll use some other term, like some other equivalent term, but that has to be like somewhere defined in this T box, right? But somewhere there has
Yeah.
to be that notation, right? We cannot use it,
Yes.
right?
Yes.
Okay, so this is
So for example, when we are constructing an ontology, right, we explicitly state that person is a class or a concept, and we'll state that human is a concept, and then later on we can then make this
equivalent.
the relationship, saying that okay, okay, I have defined person, I have also defined human, And now I'm defining this, that I'm defining that both are same, or I'm stating that both are same.
And whenever we define relationships, it includes all the relationships as well as the composite relationships also. The one like has father and has brother. So apart from like has spouse and whatever other simple relationship, complex relationships also have to be a part of our box, right?
Yes, yes, that is right.
And has spouse will have like has wife and has husband, something like that. So it is a super kind of a super class, and then has wife and has husband will be a subclass.
Okay, so in terms of how you visualize it, that is right. But these are called properties or roles, right? So this is a, you can say this is a super role or a super property, and this is a sub property. So you can have has wife is a sub property of has spouse, and you can also say that has husband, depending on the things that you want to capture, right? So if you want to capture the husband relationship, you can do that. You can say has husband is a sub property of has spouse.
So we can have more than one, and so like for example, in this case, it will be a binary, like 0 or 1 values only will hold. Like if has wife is true, then has husband will be false, something of that sort. This kind of representation can be
Yeah,
made.
you right, you can say that. You can say that, okay, if something like father and mother also, right? Okay, so you can say that they are disjoint with each other. So
Yes.
if A has father B, it cannot be the case that A has mother B. The same
Right.
person cannot be both father and mother, right? So they are disjoint. So you can and we'll talk about those different constructs later on as well. So you can also say that has wife and has husband are disjoint with each other.
Okay. And then there is this composite role, like so has father followed by a dot and then has brother. So basically we are saying that about father's brother right here. So this kind of it's a sequence that follows. From that we can create this relationship. So this order would be important in this case.
Yeah, right. You're right. Order is important. So A has father B and B has brother C. Then it is the case that A has uncle C.
Had
So
I
the
written
order,
brother and father, then it could be like parent kind. Then has a parent, something would have come. That
right? Yeah,
relationship
this
would have.
relationship will not hold. Right. You're right.
Okay, okay. Thank you. Thank you, sir.
Okay.
Just
So
one. Why is it called box?
right. Yeah, that's a good question. I don't know. I'm not aware of that actually. So I don't know. Yeah, it is. Yeah, this is like a standard thing in description logic. So we have these 3 boxes, but why is it called a box? Yeah, I haven't explored that part, so I don't know the history behind that.
All right.
Yeah, that is interesting, but yeah, I don't. Okay, so maybe I'll discuss this and then stop just this example, because I said that these are 1 hour sessions and we are already past the 1 hour, and then we can
No,
resume it after.
I think last time also we can stop when you find a logical stop. We can just stop there. Yeah,
Sure,
like
sure.
you don't
Okay.
have to. Yeah. Whatever you
So
feel
I
like is
okay.
natural pause, we can stop there.
Sure, sure. Okay. So I was expecting that this thing will spread over 2 sessions. So let me see. So maybe yeah, maybe we can um, just discuss this, because I did talk about the first order logic mapping, and then I can come back later. Okay. So um, again, so this is just meant for mapping this description logic syntax to the first order logic, right? So in description logic, we simply say that woman is a sub concept or subclass of person, and this is the concept subsumption. But everything that you write in description logic can be translated or mapped to first order logic, because as we discussed, it's just a subset of first order logic, right? So okay, so in first order logic, you have this particular, you use implication. So there's a, whenever there is a subset or subclass, in terms of set theory, this is a subset, and in terms of first order logic equivalence, this is the implication, right? So this is for all x. If x is a woman, then it also means that x is a person, and this is the binary relationship that I was talking about earlier. So if has wife is a subproperty of has spouse, then So if X is related to Y has Y, then it is also the case that X and Y are related by the has-spouse relationship. Okay, so we can stop here, and then I'll come back to the quantifiers in the afternoon. So we can discuss more of these constructs, quantifiers, and the union, intersection, the cardinalities later on. Right? And we can stop here, like I said, and we'll resume. So that's at 3 o'clock. So we'll meet again at 3 p.m. And in the meanwhile, maybe if you can explore this further, and then just if you have questions, we can discuss in the afternoon, right?
Yeah.
So that is all for this session.
Yeah, you want to take a couple of questions now?
Yeah, sure. I can take some questions.
I just wanted to say one thing. Today afternoon, I have to go for a lecture. I won't be able to attend. So would it be possible for you people to share recording? I will like view it.
Yeah. Vandita, we will
Nice.
share the recording in the evening. We will
Okay,
share the
great.
recording in the evening.
Great.
So you will be able to. I also have a meeting in the afternoon. So, but Shankar will be there, is what he told me in the morning.
Oh,
so
is it
he'll
okay?
be there.
I thought he's not here for that.
Great.
Yeah, sure. I can share the slides as well as the recording.
No, yes. No, but it will be saved in the cloud.
As part of, okay.
So when you record, you have to record to the cloud, yeah?
Right.
Oh, so yeah, Shankar will not be able to attend today. So I think Vinod, can you take care of the recording part then in the afternoon?
Yeah, sure.
Yeah, I can start the recording again.
Right?
Yeah, so please make Vinod co-host, and he will take care of